Good afternoon for everybody, or good evening, or good morning, depending if you are east or west from Brazil. My name is Arnaldo de Carvalho Jr., and I will present to you the Paraconsistent neural network applied in dynamic system identification control. This thesis is based in a project of Paraconsistent neural network. I called this new neural network with this name because it uses or it runs with Paraconsistent annotated logic by two value notations activation function. And I applied this new technology to identify and control Rotary inverted pendulum. So one artificial neural is based on this design that we can see in this slide. We have a certain number of inputs that will combined in just one value. Each input is multiplied by one weight, W, and the sum also has another value that's B, like bias, resulting in a number N. This number will be the input of one activation function, and the result of the neuron analysis is the output A. We have several activation functions in the reference, but most of them you need two features. One desirable feature is the nonlinearity. This allows the neural network to compute non-trivial problems with a small number of nodes. Another feature that is not in this slide is the function. If the function is easy in terms of mathematics, the calculation process could be fast and robust. Another important feature is the function. The activation function must be differentiable. This will allow to apply gradient descent method in the training of the neural network. So, PAL2V, what is this? It revokes the non-contradiction principle of the classical logic. It means that it can handle contradictory signals. The mathematics is very simple, robust, with a few rules. PAL2V receives this name because it works with two orthogonal inputs. One input is the certainty degree, the favorable evidence degree. It has one value between 0 to 1, like analog value, or a percentage of how much these inputs answer one question. Lambda, for other side, is another input that is non-favorable to the answer. For example, if you go to the doctor and after some tests, some exams, the doctor says you have 80% that you will die tomorrow by cancer. And then you go to a second doctor and he says there is 70% that you don't have anything. So what do you do? This kind of situation is the situation that the PAL2V tries to offer one answer. In the right side of this slide, you have the main and short calculation of the PAL2V. With the inputs mi and lambda, we can calculate the value of d. D cannot be higher than 1, and as we can calculate the d, we can find mi ER, that is the output of the PAL2V analysis after analyze the contradictions between the both inputs. Okay, so the main point of my thesis is that this function attends the both features. It's nonlinear since it's a rational calculation, and it is differentiable. I present how to calculate the derivatives of this function in my thesis, and so all the rules of the PAL2V logic can be written in form of an algorithm, and it receives a name of PAN, Paraconsistent Analysis Node. So this symbol of the PAN, you can see the both inputs and some of the PAL2V outputs, and one is the mi ER that I used in my thesis. So the graph here on the right side, you can see the output mi ER depending on the values of both inputs, mi and lambda. Mi from 0 to 1, and lambda we fixed in 3 different values, 0.1, 0.5, 0.9. So you have 3 different outputs, green, blue, and red. All of them are nonlinear functions, so depending on the combination of the both inputs. So to achieve the second feature of my proposition, I present the derivatives from the output to both inputs, and with this we can apply the backpropagation classical algorithm of training to the neural network, right? So I propose this in a prototype of a Rotary inverted pendulum. The photo of the pendulum is here in this slide. It is a free pendulum fixed to an arm, and the arm is attached to a DC motor. Okay, you have, so why I choose the RIP as a system to be controlled by this new network. I choosing this because it's hard. So first, the Rotary inverted pendulum is non-linear. Second, is under-actuated system with fast dynamic. Any problem in the movement of the arm or in the motor, the pendulum will fall down. It has a 3-dimensional move with 2 degrees of freedom. So the arm moves on the horizontal and the pendulum moves on the vertical plane. Different types of pendulum systems are benchmarked for control strategies. So you have several types of pendulums. The RIP is one of them, and they are used to test identification, control, sensors, microcontrollers, or any other technologies that we used. Why it is used for benchmark? Because it's applied in robotics, in cybernetics, aerospatial research. So how the rocket go to the moon, it's based, the trajectory of the rocket is based on the pendulum control. So in the first study, I designed one simple network with only 2 Pal-2V neurons in the hidden layer. And I used, in fact, only one input of the two Pal-2V inputs. One input is fixed in 0.5. This is because in the first graph here, when lambda is fixed in 0.5, the output is a classical sigmoid output S function in this blue. And then I used some selected inputs of the RIP and the control signals, and I try to do this simple network to learn or approximate to a function of interest. In this case, one network would learn the function of the arm angle, a second neural network would learn the function of the pendulum angle, and a third network would learn the control signal. Okay, so I also compared this paraconsistent neural network with some equivalent classical network with standard activation functions, and we could see the results here of the mean square error. So the PNN had faster number of epochs and achieved a low level of mean square error compared to other classical functions. So the performance was more or less close to the HELU, that is one of the faster activation functions in the neural network theory. Second, here we have the results of the learning. First figure, you can see the real arm angle signal of the pendulum in red, and in blue the PNN1 output, very close the result. The second, from the pendulum angle output and the PNN2, you cannot see any difference, and the control signal U and the PNN3, also very difficult to see any difference between them. I also removed the control that I used to control the pendulum for the learning process, and I swapped it by the PNN3 taking the control, and the PNN3 assumed the control of the pendulum, and I tested the robustness of this system. In fact, I did this because the reviewer of my article requested me to present it in the article. It was not in the article in the original version. So I applied some disturbances directly in the pendulum, some kick disturbances in the pendulum, to see how the control reacts to them. And the algorithm of the pendulum has some constraints. One constraint is the limit, the maximum peak of the control signal. That's +1 and -1. And you can see here that after the disturbance applied directly in the pendulum, the control go and the saturation point. But even if with that, the system recovered the control of the RIP. The results of this preliminary study was published in a IEEE Access journal, as you can see the reference here. At the continuity of the study, I performed a full control of the RIP. In this case, I proposed a control based on the model reference control architecture, using 3 networks. One network for the controller, and then one network to model the arm angle, and another network to control the pendulum angle. All the networks should be recurrent to use time based signals. So the inputs of the recurrent paraconsistent neural networks are delayed by 1 sample time. It means that the network now are receiving delayed inputs and must predict the next output, so more difficult to do in this case. Okay, so now I used both inputs of the PAL2V. The MI inputs are receiving the delayed signals of interest, and the lambda input are receiving the feedback signal from output of the neural network, also delayed by 1 sample time. I use the identification model NARCS to do that, and applied a random or pseudo-random signal at the input of the system. Again, the recurrent paraconsistent neural network also achieved a good performance results in terms of MSE compared to other classical networks with the same parameters, same number of inputs, same number of weights, same number of neurons in the hidden layer, etc., etc. So from the architectural proposed design, we have here 2 error signals. One error signal is the comparison between the real arm angle and the arm angle for RPNN1, and the second error signal, EP, is the comparison between the pendulum angle and the RPNN2 output. Both signals goes to RPNN3 as input. Now we have the comparison between the controller used as the reference for the benchmark, and I designed the controller by the pole placement mode. It's also called the state feedback, stateful feedback controller. So we have the signal of the pendulum arm angle from using both controllers. You can see that the signal in blue from the paraconsistent control is more regular. This situation here is based on backlash effect and the delay in the controller to receive the signals and act in the motor. So you can see this kind of backlash here, this oscillation here on the signals. Now we are using as reference a square wave. So you can see here that the shape of the figure is much clean and much uniform with the paraconsistent control than the pole placement control. Even using the pole placement control as the controller of reference to train the paraconsistent network. So even with that, the control resulted in best control. During the transitions of the square wave used as reference here, to up and down, you can see the peaks of the pendulum. So the pendulum shake a little during these transitions, and you can see again that the shake or the movement in terms of rad angle is less with the paraconsistent than the pole placement method. When we also compare the control signal, we can see that the peak to peak value is lower with the paraconsistent control compared to the pole placement. So it means that the controller effort to keep the rip under control is lower with the paraconsistent than with the pole placement. So we also performed the robustness comparison, and the pendulum angle signal here in the top, an arm angle. You can see in the arm angle the arm follow the square wave reference, but we applied some disturbances directly in the pendulum, and these disturbances in the pendulum reflects in some movements in the arm to try to absorb the impact of the disturbance and the controller trying to control the system. So you can see these peaks here in the movement of the arm. And below you can see the signal of the control. So after some disturbances, the controller loses the control of the rip. As you can see, the pendulum angle increasing up to 0.8 radians. That means that we need to shut down the plant, because the pendulum in fact fall down. The same kind of test performed with the Paraconsistent neural network controller. We applied several disturbances here. We can see several peaks during the arm movement, absorbing the impact of the pendulum disturbances, with some peaks some disturbances really strong, and the arm moved up to 3 rad to absorb the impact. And when you see the signal of the controller, it achieved the saturation several times, but it does not lose the control of the rip. So this technique to build a controller with Paraconsistent neural network using the architecture of model reference control resulted in a controller with better robustness and lower effort to control the system. So the results are published, of course, in my thesis and in a paper submitted to the IEEE Transactions in Cybernetics that is under evaluation right now. I would like to thank you, this audience, and the opportunity to present my thesis. And here you have my contact information, and if you have any question, I'm free and happy to answer. Thank you.